Hi, we'll cover the concept of lock in this lecture. The basic idea of lock is to ensure that any critical section executes as if it were a single atomic instruction. For example, let's consider a statement that increases the value of a balanced variable by 1. We'd like to make sure that this increasing the value balance by 1 as an atomic instruction, then what we could do is first we declare a lock variable, and then we lock the mutex, and then execute the statement and unlock the statement. So via adding some code around the critical section, we can ensure that this code is executed in atomic fashion or in mutual exclusion fashion. So lock variable contains the state of the lock state. There are two states. First one, whether it is available, or also it is called unlocked or free. So here, no thread holds the lock. And another state is acquired. It is also called as locked or being held. Exactly one thread holds the lock, and presumably the thread is in a critical section. The semantics of the lock is as follows. So it tries to acquire the lock, and if no other thread holds the lock, then the thread will acquire the lock and enter the critical section. This thread is said to be the owner of the lock. The other thread are prevented from entering the critical section while the first thread that holds the lock is there. In pthread, lock is called mutex. So this is a name which pthread POSIX library uses for lock. So it is used to provide mutual exclusion between the threads. So it first declares the lock as pthread mutex, and also we have to initialize a variable when we declare a variable. So pthread mutex initializer. And then it calls lock and unlock for the critical section. So here the capital P, this is a wrapper function the author of the textbook has developed, and then you should be able to find the code for this wrapper function easily. It's in the text. So this is a wrapper for pthread mutex lock, and then you do unlock. We may be using different locks to protect different variables to increase the concurrency and for more fine-grained lock. It is important to use efficient lock to provide mutual exclusion at a low cost. Building a lock needs some help from the hardware and the operating system. There are three basic criteria to evaluating the quality of lock. First one is mutual exclusion. Does the lock work preventing multiple threads from entering a critical section? That's for mutual exclusion. Second one is fairness. Does each thread contending for the lock and get a fair shot at acquiring it once it is free? So does it avoid starvation? That's the fairness issue. And the third criteria is performance. Is holding a lock and releasing a lock is expensive or cheap? Is it fast to acquire a lock, or is it slow to acquire a lock? That's the performance issue to determine the criteria for the quality of the locks. The first approach to implement a lock is using the interrupt. So when a thread tries to enter a critical section, it can disable the interrupts. So one of the only solutions use this approach to provide mutual exclusion. But it is invented for a single processor system. For example, lock inside the body of lock, it called disable interrupt, and unlock enable interrupt. But the problem of this approach of using interrupt in implementing a lock is it requires too much trust in the application. It is possible that once the application acquires a lock, and then it may monopolize the CPU forever. And then it does not work on multiprocessors, because if we usually we can disable the interrupt for a single CPU. So if there are multiple CPUs, processors, then still the other threads running in different CPU can enter the critical section. And the third one is the performance may not be good because the executing disabling interrupt and enabling interrupt is expensive.